Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will go through the XOR operation. It's a logical operation. It stands for exclusive OR, but for our purposes, we just need to know that it's equivalent to addition modulo 2. So the XOR operation is written like this. It's like a plus sign with a circle around it. We use this to encrypt messages. So computers use binary. They represent letters as 8-bit strings like this. So 8 bits means it has 8 binary digits. So how you represent a letter as an 8-bit string comes from the ASCII table. That's just a table so no one gets confused, so that everyone, when they're encrypting and decrypting, use the same string for A, the same string for B, etc. So that table's in the notes, so you can easily look it up in Google. So this is how L is written according to that table. So what we do is we take this 8-bit string and we're going to XOR it. So we can use XOR as a verb. We're going to XOR the letter and some key. That will allow us to encrypt the data. So let's start. We're going to go 0 XOR 1. So this is like addition modulo 2. So that's 1, 1 XOR 0. It's basically like 0 plus 1 gives 1. 0 plus 0 is 0. That's all normal. The thing that's different, because it's addition modulo 2, 1 plus 1 is equivalent to 0 modulo 2. We don't do any carrying here. So 1 plus 1 is 0 in modulo 2. So 0 XOR 0, 0 XOR 1, and here we have our ciphertext. Now this doesn't actually correspond to any of the characters in the ASCII table. But that doesn't matter. It doesn't matter if we can't actually encrypt this into another letter, because computers display and store the encrypted data, the ciphertext, as a long string of these numbers. Now, sometimes instead of in binary, they will display it in hex. So in hex, we have a 1 in the ones column, then we go 2, 4, the next one is in the eights column, no 16s, then we have 32, 64, and 128. So this number here in binary, if I were to represent it in decimal, I just add up all these numbers, I get 233. So that's in base 10. If I want to convert to hexadecimal, I don't mind if you use a computer for this, but this one needs to have 14 16s. 14 times 16 is 224 plus 9 left over. Remember, we represent 14 as a digit E in hex, so it'll be E9. Usually you have a 0x at the start to indicate this is a hex number. So the computer often displays the ciphertext in hex just because it has fewer digits. I mean, this one here, you can see if you had a message that had many letters, each of them has 8 bits. That's a lot bits. This is just usually easier for humans to handle. But you can see the XOR function is really easy to implement. The fact that there is no carrying makes it very computationally efficient. But XOR is not secure in and of itself. This is basically just a simple shift. So one of the reasons the algorithm I showed in the previous slide is not secure is I used the same length for the key and the character. Both were 8-bit strings. And that would mean that each letter is always mapped to the same letter, which means someone could use frequency analysis. It also wasn't secure because the key being only 8 bits, there are 2 to the power of 8 or 256 possible keys of 8 bits. That's actually not a large number for a computer to try. But there are two systems that use XOR, DES and AES. DES uses a 56-bit key. So there would be 2 to the power of 56 such possible keys. That is an enormous number to try. AES uses even longer keys. Now, DES is like the old system from the 70s. It's been replaced by AES. So this is pretty much not used anymore. AES is a symmetric crypto system, as is DES. So there is only one key. It is a long binary string, a long bit string like we saw on the previous slide. And we can see from the previous example that XOR is very quick to implement. So that's the benefit of doing cryptography like this. But in order to provide security, these two, which are algorithms, they don't only use XOR like I showed you on the slide. They also do other things. For example, they permute the data, they switch around zeros and ones, they divide the data into blocks, they sometimes switch around those blocks. They do all sorts of things, but the XOR is an important part of both of those algorithms. And we're always XORing some sort of bit string to a key, and the key is just like the key I showed you on the previous slide, but it is longer. So where are these keys stored? I mean, if someone's going to use a key to decrypt it, they need to know the key, and they can't keep it in their head because these keys are extremely long. So sometimes it's stored on servers. They're like computers to which you connect. Like if you log on to Facebook, you're accessing their server. But if a key is stored, it's never stored in plain text. It is encrypted itself. Sometimes as part of the algorithm, the keys will be deleted straight away, and then keys might get used later on. See, what actually happens here is there is a bit of a problem. This algorithm, although it's a very complicated algorithm, it takes the computer no time at all to encrypt data. But there is a problem with the security of the key. So sometimes what servers will do is they will send you the key using public key cryptography that we'll learn about in the next video. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.